Okay, so today I'm going to show you how to do an optical heat flux calculation in Heat. So we're assuming that you already have Heat installed, you already know how to run it. This video is going to show you how to run the optical approximation from the GUI. Just to be clear, the optical approximation means power flows along the magnetic field lines. So I'm showing this image here. This is from this nuclear fusion paper. It's a gyro orbit paper about heat, but it has this figure, and you can see the magnetic field line in yellow. And what we assume when we say the optical approximation is that power is flowing along this magnetic field line. It is not following this helical trajectory that's associated with the cyclotron motion. So this will be true for electrons usually, because they have such tiny Larmor radii. But for ions, you may need to include the gyro orbit trajectory, and that'll be a different video. But for today, we're going to follow the optical approximation, and that's how we're going to do our calculations. There is a folder that contains the test case. So I guess I should show you where that lives. On the Heat GitHub page over on the releases, there is this test case. And so this contains CAD and some input files to run a test case. So you should grab that, and if you extract that, you'll see inside of it there's this batch file. That's for running in terminal mode, which is not this video. And then inside this NSTX directory, there are some GEQ disks. These are all the same GEQ disks, just copied with different time step numbers: 4 milliseconds, 50 milliseconds, 200 milliseconds. And then there's some other input files, notably the input file with all of the data about the run, and then the PFC file, which defines which PFCs we're going to calculate our heat fluxes on, and then this CAD file, this step file. If we look at the step file, we can see it looks like this. I'm going to hide this for now. The PFC of interest today is this tile I've highlighted in yellow. This is the lower diverter of NSTXU, and this is the flat inboard diverter horizontal target. And this one's called 843, solid 843. We also have 842 and 4 here. So the reason we need to include these when we're doing this calculation is because power will be flowing from right to left, and it will cast a magnetic shadow onto this PFC surface, 843, depending upon the fish scale and the way that power is flowing. So there will be magnetic shadows cast from this tile onto 843, as well as 843 onto itself. And you can see here the fish scale there that will cause a little bit of a shadow to appear here. Furthermore, we have this plate underneath the IBDH. This I've put in there to simulate a carrier, a tile carrier. You could put the real CAD for the carrier in, but the beauty of putting a plane in is that you only need 2 mesh triangles. This plane, when it gets meshed, is 2 mesh triangles, whereas a full CAD model of a carrier could be thousands. So that it makes the intersection calculation faster. And then this gyro source plane you saw before, this will be used for the gyro source algorithm, and so we're going to have it turned off for our optical approximation algorithm. It's basically a plane that we launch macro particles from the kinetic theory distribution functions for gyro orbits, and so for optical approximation it's not needed. So that's the CAD. Our goal is to calculate the optical heat flux on this tile, this 843. So that'll bring me to this, oops, that's the heat CAD class. I'll just close that. That'll bring me to this input file. So there's going to be a separate video that just goes through all the values in this, and I'm going to add a separate page on the tutorials, or on the read the docs, that sort of outlines every variable here. But what we do need to look at here is this PFC file, so pfcs.csv. There's a sort of description of everything in here, but the short and sweet is there's columns here. This is a CSV, so there's columns, time steps, PFC name, resolution, div code, intersects, and excludes. And then this is a line that will be used for that solid 843 object. So we're going to calculate all the heat fluxes between 0 and 5,000 milliseconds. We are going to calculate them on solid 843. That directly is the name that corresponds to the CAD file, the STP file. We're going to mesh that object with a resolution of 5 millimeters. That's to say no mesh triangle will have an edge length longer than 5 millimeters. We are going to say that this is in the outer diverter, in the lower diverter. So that's the diverter code, is lower outer. We are going to use all the objects in the CAD except for the gyrosource plane in the calculation. Like I said, this gyrosource plane is only for the gyro-orbit algorithm. So if you included it in the simulation, you just end up shadowing this whole PFC basically. This is what we're going to run, and then we need a heat GUI to do that. So I've already launched the GUI here just by running you can run it from the Docker container. This is the development machine, so I'm running it just from my terminal. And once you have that running, you can just go to the GUI at the address here. You can change the theme if you want, to be, light or dark or, whatever kind of these crazy colors you want. I'm just going to go with the default, which is slate. And then I'm going to go NSTXU. I'm going to take my input file here, and I'm going to drag and drop it in just to populate all the fields that I need. You don't have to do that in the GUI. You can actually just go through these tabs and fill it out, but that's the fastest way. Then I'm going to go to the MHD tab, and we can see shot number is 204118. That needs to match, if we have our G file in this D3D format where you have a 6-digit shot number followed by a 5-digit millisecond number, this shot number needs to match this, or else it'll give you an error. And then your bounds of minimum and maximum need to be outside the bounds of your equilibrium. So I'm going to choose 2 for this. We'll do a steady state pulse. Like I said, these are the same equilibria, just copied with the name changed. So I'm going to copy those in here, and it loaded them, we can see. And I'm going to load it just so we can have this, so we can see it. So like I said, so this is the IBD H surface. This is the surface of solid 843, so the strike point is landing right on that surface. The trace distance is how far we are going to trace from the surface. So if I open this, if I open the CAD model, I can basically start from every surface on this, and I'm going to trace out 10 degrees or 20 degrees or however far I say in that input box. The trace distance input box is how far I will trace. So for really shallow field lines, you might need to go further. For really steep ones, you might not, but that's a user input. So you basically, 10 will be enough to start this. And then this is the step size of each step of integrating up the field line. So if you have very shallow field lines, you might want this to be lower. But it could even be, honestly, 1 for just a basic NSTXU simulation. Excuse me. So this is basically how far will each, we discretize the curved magnetic surface, the curved magnetic field lines, into steps that are this wide in toroidal angle. So anyways, we have this all loaded. That's great. We already hit load MHD, which is how we got this plot populated. We're going to come down here to the CAD settings. I'm going to load these. This is the intersection resolution. So this is the region of interest. This is we defined this resolution in that input file, pfcs.csv. The box that I am filling in now, this intersect resolution, is everything except that. So this CAD object, this CAD object, and this CAD object. And so we're just going to use standard, which is a default in heat, and that will give us a pretty good mesh that has a low number of triangles but a high fidelity representing the surfaces. So I'm just going to take this step file, drag and drop it in there. It'll take a second. If it's a big file, it could take like a minute to load. So it's loading. We can see in the heat GUI that it was loading. If it's taking a long time, look in the GUI and make sure that it says this, that it's loading the step file. Okay, so this CAD settings box is done, so we can come down to the PFC settings. We're going to load in this PFC CSV file, and all of those columns I described before are there. I'm going to load it. So that just built STL mesh objects from the CAD, and it's done. And then I'm going to come to this optical heat flux setting. So for this example, we're just going to do a Gaussian spreading, which is an Ike profile. There are some other options here, like you can do it from a file or from like a Dan Brunner multi-exponential, but this is going to be what we're going to do today. Excuse me. And so I'm going to use this Ike number 15. That's the default. This is the Ike regression number 15 from his paper. If you want to find the reference, it's in the source code. And then we're going to use this Minkowski scaling, which is for NSTXU. This is figure number 6 from that paper, also in the source code. And then there's a heat flux width, user-defined Gaussian spreading. If I would have chosen user, these would override the Ike profile. But because I have Ike selected, whatever I put in these boxes will be ignored. This is just a background heat flux that gets added on. This is a Greenwald density fraction, which you need for the Minkowski scaling. Yeah, and so the power injected is 10 megawatts for this case. And then we're going to say this fraction of the power is radiated away in the core. So basically 10 megawatts is injected, 7 megawatts is going to be conducted down to the target if I use these settings. And then these are the power sharing fractions between the diverters. Remember how we marked back here lower outer for our div code. So our lower outer power fraction here is 0.7. So this will take 70% of that 7 megawatts and conduct it to the outer target. I'm going to load all of those settings. I'm going to come over here and I can see that this is checked. It's maybe easier if I look in a different theme. Let's do this one. So this is checked, this heat flux point cloud. And the output file settings, we have point clouds, we have mesh files, and we have CSVs. I'm just going to select all of those for this run. I'm going to run it. It'll just take a few seconds. It's doing all the traces you can see. And it's done. Sorry, I'm coughing. I've done these videos for like the past 2 hours, so my voice is getting a little hoarse. Something to note in the output is that this tessellated diverter power is if we took the power that lands on this mesh object and we multiply it by the ratio of this toroidal width over 360. So basically we scale what's here to 360 degrees around the machine. That is this number. So the theoretical number of power is integrating the Ike profile, the heat flux profile. This is scaling what comes out. So this is power balance that we're looking at. So what we can see is we're pretty close in terms of power balance here, like 10% or so. So that's pretty decent. You can increase the fidelity of that by increasing your mesh resolution. There's all sorts of things I talk about in some of the heat papers to do. Let's go look at the results here. So I'm going to open ParaView. This is assuming you already have ParaView. I'm going to open go to the heat data directory. I'm going to go to my NSTXU folder. I'm going to open the STLs for solid 843. This is the 5mm one I just built. And there it is. So again, we can see that our mesh elements are no longer than 5mm on any side. I'm going to change this to be a little darker. I did that in the edit color. I'm going to change it back to just a surface, so no mesh edges. And I'm going to show you what each of these files that we have are. So for this run, we did 2 time steps, 50 and 200. And so I'm going to look at one of those where I have my ParaView. I'm going to go back up to the data directory, NSTX 204118, and I can do 50 or 200 here. Let's do 50. I'm going to open ParaView, and I have a point cloud and a mesh. So remember, we did a point cloud and a mesh, so that's what these are in the ParaView directory. They are both. So let's open the point cloud first, the heat flux optical point cloud. I'm going to apply that. I'm going to change the color bar to be, capped at, 10 megawatts per meter squared. I'm going to make these points, and then I'm going to change them to be a little bit bigger. Let's do 4. And we can see that they start showing up like this. That is what we're looking for, a profile like that. Note that this is loaded on this corner. That's because we didn't include the CAD objects that are right here. We only included one poloidal location of tiles. If we would have included the next tile over, that would have protected this. So you want to see that. That's actually good because it shows that the we're not getting shadows cast there where there is no CAD. And we can see that the bottom is good. These will go away if you trace to 20 or something. So this looks pretty good. So something like this is what you're looking for. I'm going to show, we can change this to be a mesh. And so this is the mesh version of the output. So you can do that, and it contains, we can turn off this now too. This contains the full mesh as well as the coloring. So it just colors each item by, so the point cloud, as we can see, if I put that on, is at the centroid of every mesh element, whereas the mesh element just colors the entire mesh element as one color. So yeah, so that's basically how you do a simple optical calculation. So this is the optical heat flux. We can also do a thermal analysis here. If we come back here, I can open the open foam settings, and so we did 50 and 200 milliseconds. So I'm going to go ahead and say 0 to, let's do 250 milliseconds is what I'm going to do. So open foam is temperature, if you don't know. So the open foam thermal analysis is what we're loading here. So 0 to 250, we'll run it a little bit longer than the width of our steady state pulse here. And we'll just do this simple 1 to 2 mesh refinement level. So if you increase this number to like 5, that'll make it a finer mesh, like a better representation of the CAD. And you can also bring this one up. This is basically the number of iterations it's going to try to match the surface when it builds a volume mesh out of your surface mesh. So if the minimum is 3, it takes longer. So this could take a significant amount of time. So for this simple example, I'm just going to do 1 to 2, but you can increase those. This one always has to be lower than this one. STL scaling we can leave. I'm going to change the time step size to be 0.25. So we're going from 0 to 250. I'm going to say every 25 milliseconds run a thermal diffusion equation and calculate temperature. Your time steps here, right? Your time steps for your equilibria have to be divisible by this number. If I don't have this, if this was like 0.02, I would miss this time step. So it would not know that there's heat flux. So this has to be a multiple of your GEQ disks. So that is important. Anyways, I'll load this up. You can select which material you want. I'm going to run heat. I'm going to do, we already did the heat flux point cloud, so I don't need to do that. I'm going to do an open foam thermal analysis here. And I'm going to run it. And it will go, and it's, that mesh already exists, so it built it, and now it's solving through time. At each time step, prints out some stuff like the maximum flux, and then the maximum temperatures here that it's seeing, and those are in Kelvin. And these are in megawatts per meter squared, the fluxes. So yeah, so it'll finish here in just a second. It's pretty quick for this coarse mesh. And then we will look at the results. Great, so heat run completed, we're done. I'm going to come back to ParaView, I'm going to turn that off, and I'm going to open now. So in this root directory, the NSTX20418 directory, I'm going to go to open foam, heat foam, solid 843, that was the name of the PFC we're doing, and this .foam file is what I'm going to open. And I can load all of this stuff, I don't need to, I'm just going to load temperature for right now. And so here you can see it's a pretty coarse, honestly crappy mesh. So increasing that mesh refinement from 1 to 2 to like 3 to 5 would make this much sharper, all these edges and everything. But interestingly, you can usually capture the macroscopic peak temperature with a pretty crappy mesh. So I'm going to change it to be, I can do point or cell data. I'm just going to do cell for this. And I'm going to change I'm going to go to the time step where we expect the peak temperature. That is at the end of that steady state pulse. And I'm going to change the color bar to go from 300. Okay, it goes to 541. That's pretty good. You could change the color bar if you want, and you can see that the temperature, the peak temperature, matches. See, if you do cell data or point data, it looks a little bit like finer. So you can choose which one you want. Let's go all the way back to the beginning and just hit play, and it'll play through the temperature loading of that PFC. We can also come into this the GUI, look at the output tab. So it gives us all the settings that we ran, and so we can export that if we want. This is also saved. Let me open a new window. If I go to the heat data directory, the last wait, it was NSTX 20418. The last step is it saves all that data in a CSV for you if you need it. So this data will all be in that CSV, and then we can see this time history. So basically, when we loaded a 50 millisecond and a 200 millisecond GQ disk, remember, because we loaded these two GQ disks, it's saying that at 50 milliseconds, turn the machine on to that power that we defined in the input file, and keep going until the end, which the last time step is 200, and then it decays off. So OpenFOAM will linearly interpolate fluxes in between time steps. And then we see the temperature here. You can turn these off and on. So our peak temperature, like let's turn this off and we can look at this. 2711.3 is the peak temperature for 843 for that object. So, yeah, so that is how you run an optical calculation in heat. Yeah, I don't think there's much else to cover here. So I'll just end the video and check out the gyro orbit video. There's also B field trace videos, and hopefully with those you can get started with heat. So I'll end it there.